Why Laplace matters. Have you ever looked at a complex differential equation and felt like you were staring at a brick wall? What if I told you there's a secret portal in mathematics that lets you jump out of the difficult world of calculus and into the simple world of algebra? Welcome to the Laplace Transform. This isn't just another math topic, it's the ultimate shortcut used by engineers to design stable aircraft, by surgeons to understand heart rhythms, and by tech giants to process signals. In the next few minutes, we're going to master this portal. You'll learn not just the how, but the why, and we'll walk through a full example that makes it all click. Let's dive in. The core concept: moving domains. To understand the Laplace transform, we need to think about domains. Usually, we work in the time domain, where functions are written as f of t. But solving equations here often involves messy derivatives and integrals. The Laplace transform, denoted by the script letter L, acts like a bridge. It takes our function f of t and transforms it into a new function, capital F of s. This S-domain is the complex frequency domain. The formal definition is the integral from 0 to infinity of f of t times e to the power of negative st, integrated with respect to t. But here is the magic: in this new world, differentiation turns into multiplication and integration turns into division. It's like turning a complex puzzle into a simple addition problem. If you're finding this math portal concept helpful so far, please hit the like button and subscribe to the channel. It helps us keep creating these deep dives for you. Rules of the game, key properties. Before we solve problems, we need our toolkit. The most important tool is linearity. The Laplace transform of a constant a times f of t plus b times g of t is simply a times capital F of s plus b times capital G of s. This means we can break big problems into tiny, manageable pieces. Then there's the shifting theorem. If we have the Laplace transform of e to the power of a times t multiplied by f of t, it simply shifts our result to capital F of parentheses s minus a. Think of a as a slider that moves our function along the frequency axis. We also have standard transforms. For example, the Laplace transform of the constant 1 is 1 divided by s, and the transform of t to the power of n is n factorial divided by s to the power of parentheses n plus 1. Practical application, step by step. So, how do we actually use this in the real world, like in control systems or circuit analysis? It's a three-step process. Step 1. Take your differential equation and apply the Laplace transform to every term. This turns your calculus problem into an algebraic equation. Step 2. Solve for capital F of s using basic algebra. No more integration by parts or tricky substitutions. Step 3. Use the inverse Laplace transform to jump back into the time domain. We often use partial fraction decomposition here to make the expression look like the standard formulas we already know. It's a systematic workflow that guarantees a result. Deep dive, a concrete example. Let's put it all to the test with an example. Suppose we want to find the Laplace transform of the function f of t equals e to the power of a times t. We plug this into our definition integral, the integral from 0 to infinity of e to the power of a times t times e to the power of negative st, with respect to t. We can combine the exponents to get e to the power of negative parentheses s minus a times t. When we integrate this, we get negative 1 divided by parentheses s minus a multiplied by e to the power of negative parentheses s minus a times t, evaluated from 0 to infinity. As t goes to infinity, the term goes to 0, assuming s is greater than a. At 0, the term is 1. So, we are left with negative 1 divided by parentheses s minus a times negative 1, which equals 1 divided by parentheses s minus a. And there you have it. A complex exponential growth simplified into a clean algebraic fraction. If you want to see more examples like this, or have a specific problem you're stuck on, let me know in the comments. Don't forget to like this video and subscribe to join our learning community. See you in the next one.